Now, dear students, once again, welcome back in new session, session 7 of electricity, class 10. In this session, we are going to discuss electric power. So, electric power in this session, we are going to discuss. And power you have discussed, power or mechanical power you have discussed in which class? In class 9. Which chapter? Just try to recall. Yes, work, energy and power. In that chapter, we have discussed power. Now electric power, how it is different from mechanical power. This we are going to discuss, and how it can be calculated, right? How it can be calculated. This we are going to discuss in this session. And I'm sure that you will enjoy because it is very important topic, and we are using appliances daily. We are using number of appliances in our in our daily work. So this is very interesting. Now let's start. Dear students, before starting electric power, we are going to just discuss power only. And power we have discussed in class 9 in work, energy and power chapter. And here we know that work is said to be done when force is applied on a body and body undergoes a displacement, right? So here we know that when work is done, we have nothing to do with time, that in how much time the work has been done. Only work should be done, right? Sometimes work is done very quickly, sometimes work is done rather slowly, means sometimes you take some time to do work, and sometimes you do the work very quickly. You must have seen some example from daily life that two people might do the same amount of work, but even then one is said to be more powerful than other. One is said to be more powerful than other, though the work done by both of them is same. So I'm taking one example here. Suppose you and your friend, okay, both are asked to lift a load of 20 kg to a height of 1 meter, one by one. First, you are asked to lift the load of 20 kg to a height of 1 meter, and after that, your friend is asked to lift a load of 20 kg to height of 1 meter. Now, how will you come to know that who is more powerful? Who is more powerful? But the work done in this case, work done here, because you are lifting the load, so mgh, okay, gravitational potential energy means work done will be in the form of m into g into h. Work done by both of you is same here. But who is said to be more powerful? How will you come to know that who is more powerful? So here to decide that who is more powerful, we need another quantity that is known as time. That is known as time. So who is lifting the load in less time? Okay, if you are lifting the load in less time than your friend, then you are said to be more powerful. So the quantity that has to do with the rate at which a certain amount of work is done is known as power. So power is the rate at which work is done, right? And here we have studied in class 9, it is the power is defined as the ratio of work to the time. So that is mechanical power, because mechanical work is being done. You are lifting the load, mechanical work is being done, and we have discussed about many formulae of work done here in class 9, and therefore mechanical power. And that is work done can be 1 by 2 mv square, work done can be force into velocity, right? So now in class 10, we are going to just add one word to this power, that is electric power. Electric. So now we are going to discuss electric power in class 10th. In electric power, now let's see what is electric power. Now, before starting this new topic, I'm taking one example. If you have made a electric circuit, and in that circuit you have used one key also, and along with the wires you are having one small bulb. And if you want to glow that electric bulb, what do we need? What do you need? Or I am using here, we need. So what do you need? So you need a cell. You need a cell or a battery. So that is electrochemical cell or electrochemical battery, right? Electrochemical means chemical energy is being converted into electrical energy. A cell or battery, it converts chemical energy stored in it into electrical energy. Therefore, it is called electrochemical cell or a battery. What is the function of cell here? So cell does work upon a charge because it is providing electrical energy. Electrical energy, it is the flow of charges. So it does work on charges. Which are electrons? Okay, free electrons. So to move it from low energy to high energy terminal, right? High energy terminal. So here the work done on the charge is equal to electrical potential energy. Electrical potential energy change of the charge. As in previous example, when you were lifting the load from the ground to a height of 1 meter, from 0 to 1 meter. Here same charge is the equivalent to the electrochemical energy change of the charge. The change of charge is there from low to high. So thus electric power, like mechanical power, is the rate at which work is done. So like current, power is a rate quantity. It is also a rate quantity. So power in case of electrical appliances, when we are using electrical appliances, that how much electrical energy it is consuming, how much electrical energy is being consumed by a circuit. So electric power is defined as the amount of electric energy supplied to a circuit or consumed by a load. When I am taking example of this here bulb, the bulb is a load. So at home, when you are using a refrigerator, microwave, electric iron, other appliances, so these are called load. These are called loads, right? And this again I am defining. It is defined as the amount of electrical energy supplied to a circuit or consumed by a load in unit time. So electric power, like mechanical power, it is here in electric power, it is work done on charge upon time. So formula is almost same, but here work done on the charge. There mechanical work is there, mgh, it can be m1 by 2 mv square f into v. But here it is a work done on the charge. In mechanical power, work is done on the object, right, or by the object. So electric power, it is also written as work done means energy consumed by the load or the circuit. Electrical energy consumed by the load or the circuit. How much electrical energy is being consumed by the source, which is being supplied by the source of electricity. That may be cell or a battery, right? Other source. So electric power, its formula here comes out to be P is equal to E upon T. E is electrical energy consumed. So this is very important to remember. Remember that how electric power is different from mechanical power. Okay, how its formula is different, right? So I am sure that you must have understood here electric work done on electric charge. Charge means charge here, it is a flow of electrons here. How much electric energy is being consumed. Right, now we are going to find different formulae, right? Now in earlier sessions we have discussed that work done by electric current I, when it flows for time t, when potential difference V is applied, okay, it is work done is given by V into I into T, because we know that this W is equal to V into Q. V into Q. V is a potential drop applied by the source of electricity. Electricity, right? So here power in place of this W, so because we know that we have studied power is equal to work upon time. So in place of W, what we can write here, W can be replaced by V into I into T. So here I am replacing V into I into T upon T is there. So you know T cancel. So when these T and T cancelled out, right? What is left here? This T is cancelled out with this T. Right? What is left? V into I. So electric power here, its formula, we get one formula that P is equal to V into I. This means power is also the product of potential difference and electric current, amount of electric current. So this is one formula. Electric power is equal to potential difference into electric current, or we can say magnitude of electric current. Rather we should say magnitude of electric current. Now, generally, you must have heard from your parents if you are asked to buy a LED from the market. So, if your father is asking, "Beta, go and buy one LED from the market." So, before going to market, you ask one question to your father, "Papa, of how many watt?" Okay, LED of how many watt? Then he says 60 watt. 60 watt. So what is 60 watt? What does it mean? We shall be studying here, right? 40 watt, 60 watt, 100 watt. Now, next. Now, if an electrical appliance is operated at a potential difference of 1 volt here, this is if V is 1 volt and it is carrying current of 1 ampere, then power become 1 watt. This 1 watt is a definition from this formula. 1 watt is a definition of from this formula. So here from this formula, P is 1 watt, V is 1 volt and I is 1 ampere. So here we get formula of 1 watt, 1 volt into 1 ampere also. This is a the relationship between watt and voltage and ampere. And other bigger unit of watt is kilowatt, and 1 kilowatt is equal to 1000 watt, right? And this is one more unit, 1 horsepower is equal to 746 watt, and if we convert into kilowatt, then it comes out to be 0.746 kilowatt. So from here, from this formula, we can define 1 watt, that it is electric power. Electric power is 1 watt if 1 ampere of current is passing through a circuit having a potential difference of 1 volt. It is very easy, no need to cram, very easy to define using this formula. So electric power is 1 watt, electric power is 1 watt, this way we can relate. If 1 ampere, I am taking it to this, 1 ampere electric current flows through a circuit having potential difference of 1 volt. Now coming to here. So this way we can define 1 watt. Now next. Now some formulae of power. Means power in terms of not only V and I, in terms of IR, in terms of V and R. The first one is power in terms of I and R. So here what do we see, that power is equal to V into I, this we have studied. So here this V can be replaced by using Ohm's law, that V is equal to IR. So simply when we put here V in place of V, IR, we get V is equal to P is equal to I square R. The power, electric power is equal to I square R. This is the first formula to get power when we are given magnitude of electric current and resistance is given. We can calculate power. Or when we are given power and we have to calculate I and resistance is given, resistance of the circuit or appliance is given, we can find here, right, I. So now in power in terms of V and R, again we know that P is equal to V into I, and here this I, now we have to replace I. Here we replaced V by IR. Now we are going to replace I here. So very simple here. Since by Ohm's law I is equal to V upon R, so this now I is equal to V upon R. So in place of here I, we are going to write V upon R. So when we write in place of this I, when we write V upon R, how do we solve it? Then we get this is P power is equal to, now here bracket, and in bracket what do we write? I in place of I, V upon R. So here this is V and here R is there. So this way you should practice in your notebook. You should write down in notebook. So this we get, and here into R, into R. So you can see here V upon R square and here into R. So this R into R and here R, the one R is cancelled out, and what do we get? P is equal to, electric power is equal to V square upon R, voltage square upon resistance square. Or from this we can get one more formula, resistance is equal to V square upon P, voltage upon power. So if voltage is constant and in electrical appliances at home when we are using different appliances, the voltage is constant here, right? V is constant here. Then R is inversely proportional to power. So this is very important formula. This is very important formula. Some numericals you can solve without going for mathematical application, right? Without using mathematics you can solve the numericals. It is very important to solve multiple choice questions in competitive exams. And we shall be discussing numericals in last session. So R is inversely proportional to P. Condition is this: V is constant here. So if power rating of a electrical appliance is high, then resistance is less. If power rating of an appliance is less, resistance will be high. Inversely proportional to right? So if it is more, it is less, it is less, it is more. Now, when two or more appliances are connected in series, two or more appliances, here three appliances are there of different powers P1, P2 and P3. Then their combined power is equal to 1 upon P is equal to 1 upon P1 plus 1 upon P2 plus 1 upon P3. You should try to solve it. How this relation is there? How is this relation there? Some of you must be thinking that how we have got this relationship. I shall be discussing. So if n number of appliances are there, here three appliances are there. If in place of three, n appliances are there, then power of series circuit, power of appliances in series will be total power applied to the total power upon n, total power upon n, right? So when n number of appliances of same power, it is very important to know means same power. If 30 small bulbs are being used, each bulb is of 2 watt. So then 2 is the total watt upon 30. 30 is the number, right? If 60 watt LEDs are being used, 60 watt LEDs are being used and number of LEDs are 50. So then it will be 60 watt. So 60 upon n, 50 is the number. So n in place of n, 50 will be there. When two or more bulbs are connected or appliances are connected parallel, then P is equal to total power is equal to P1 plus P2 plus P3, right? So now we are going to see and I shall tell you how to get it. Some of you should try to solve it in the meantime. Now, so net power of series combination of appliances, this formula again it is being repeated, 1 upon PS is equal to P1 upon P1 plus 1 upon P2 plus 1 upon P3. In series combination we know that resistance R equivalent resistance RS is equal to yes, it is equal to, yes, start writing in the notebook. It is R1 plus R2 and R3 plus R3. If three appliances are there, R3. These are three appliances connected, resistance R1, R2, R3. And we know that R is equal to, we have just studied, R is equal to V square upon P. V square upon P here, right? This we have studied. So therefore, from this we have got this. So in place of R, we shall write down here V square upon PS, V square upon PS. In place of R1, V square upon P1, and in place of R2, V square upon P2, and in place of R3, V square upon P3. And then you solve, then V square is common, you get this relationship, right? So this way we can get, no need to get confused. And if n number of appliances same power, each is of same power are connected, then we get PS is equal to P upon n. Again, it is important to solve multiple choice questions. So these two are important. Now next, if same appliances now are connected in parallel, then what will happen? So then this total power P for this P is representing parallel and this capital P, it is representing power. So combined power will be equal to P1 plus P2 plus P3. Again, using that formula, when a number of resistors are connected in parallel, we find this value. In parallel combination, we know that 1 upon Rp here is equal to 1 upon R1, 1 upon R1, and then 1 up plus 1 upon R2, and so on, 1 upon R3. After this, 1 upon R2, and then 1 upon R3. Yes, you can write. So in place of R here, in place of R, it will be V square upon P, and P will go in numerator. So we get this P1 plus P2 plus P3. Just solve it and you will enjoy it. You will gain confidence also. So if n number of appliances have the same power P, if number of appliances are suppose 20 and power of each one is 50, then it will be total power will be 20 into 50. 20 into 50. What I am just teaching you, you should try to write in the notebook, and you will learn more with more knowledge, with more confidence, right? Now, next. Now, numericals on heating effect of electrical we shall be doing in a separate session where only numericals will be discussed. Numericals on electric power and heating effect of electric current will be discussed in a separate session. Now, at the end, let us be grateful to the people who make us happy. They are the charming gardeners who make our soul blossom, right? Thank you with these lines.